Okay, so here's everything that we have to talk about. We're going to talk about linear regression, the linear regression model, which is stuff you guys already know. The only stuff that's new from section 1 is the concept of error. So we're going to talk about the basic assumptions, and then we're going to look at output. So this is, well, we're going to start with a review of chapter 5, which was the beginning regression stuff we did. This is on page 7. So on the top of page 7, you guys have this data set, and the data set looked at the question number and the percentage of students that answered that question correctly. So that's the data set. This is the scatterplot. So as a reminder, scatterplot is the graph for bivariate numeric data. So two variables, in this case question number and percentage correct. And they both have to be numeric. Do you guys remember how to describe a scatterplot if I ask you to? FUDs. So F is for form. So what would we say about this? Linear. Linear. For form, you really only have two options, linear and nonlinear. What does U stand for? Unusual. Is there anything unusual? I would maybe consider this point unusual. But other than that, I wouldn't say that there's anything else that's unusual. What does D stand for? Direction. Direction. In that case, what's direction?
Slightly down.
Negative. Negative. So your options are positive and negative. So this has a negative direction, which means generally, as question number increases, the percentage correct decreases. Bless you. And then what is S?
Spread.
Oh my gosh, no.
Spread.
Strength, yeah.
Strength.
Right.
What would we say the strength is?
Fairly strong.
I say moderate.
I would say moderate, moderately strong. So we would say there is a moderately strong negative linear relationship between question number and percentage correct. Generally, as question number increases, percentage correct tends to decrease. Okay, so F, form, U, unusual, D, direction, S, strength, not spread or shape. Okay, so then this is the output that you guys have. Okay, a lot of stuff we have to review on this one. Okay, so first thing, it gives us the Pearson correlation coefficient. So this is the R value. It's negative because there's a negative slope. So that should make sense. Okay, this is what else you have to remember. Do you guys remember Y hat? What that means? Predicted Y. So Y hat is A plus BX. Do you guys remember which one you have to find first, A or B? B. Do you remember the formula for B?
It's in our thing.
R times SY over SX. Okay, in our case, it gives us question and percentage correct. So question is our X, so percentage correct is our Y. It's based on the scatter plot. So the R value is negative 0.641. SY, so that's this column, standard deviation, is 14.90 divided by SX is 10.25. Negative 0.932. You guys remember the formula for A?
Something with B in it.
Correct. Very close. Y bar minus B times X bar. Our Y bar, that's going to come from here. So 68.09 minus negative 0.932 times 18. So this ends up being 84.86. So we end up with Y hat equals 84.86 minus 0.932x. Do you guys remember that you have to define x and y? Vaguely, yes. So x in our case is question number, y hat is predicted percentage correct, you have to make sure that when you define y, that you define it as something that is predicted. Okay. Other things you need to know: minimum Q1, median Q3, maximum. That's for both data sets. Do you guys know what the standard error is? It's S over root n. So you guys have that on a quiz. Here are your two sample sizes. Are they always going to be the same sample size?
Yeah.
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 Yeah. Why?
Because it's plot like. I explain it.
Why do they have to be the same sample size?
Isn't it the same sample?
Because they're like.
Because it's a bivariate data set. So you're taking two measurements from the same observation. That makes sense what I'm saying? There's an X and Y. Okay, so this is R, this is our correlation coefficient. This R value, does that indicate weak, moderate, or strong? Moderate. What is the range for a weak association? 0 to 0.5. Moderate is 0.5 to 0.8, and strong is 0.8 to 1. And it can be positive or negative based on the slope. Do you guys remember all this?
Yes.
Yeah? Why does this always happen? I think so. Okay, the other stuff that we need to review for this section, or this chapter, do you guys remember residual plots?
Yeah.
Yeah, do you remember extrapolation?
Yeah.
Extrapolation, yes, residual plots.
Okay, well, we're gonna review both anyway. Okay, there we go. Okay, so this, you have maybe on the next page? Yeah, this is what you have at the top of the next page. Okay, so this is a different type of output than what we just looked at. So this is at the top of page 8. So in this case, you have question, which is going to be your x, and then you have your constant. So if you remember, this is your slope. And this number is your y-intercept. And then they gave you the question number or the equation above. So in general, when it says constant, this is going to be the value that doesn't have a variable. Because this is our variable, this is the coefficient of that variable. You guys also saw something. You saw nonlinear output or polynomial output that looked like this. You guys remember when it had like constant, question, question squared? And then it had 3 different values? Any idea what I'm talking about? You guys are looking at me like you have no idea what I'm talking about.
I didn't hear what you said.
And then it was something like this. So in this case, this number is the coefficient on x squared. This number is the coefficient on x. This number is a constant. You guys have no idea what I'm talking about, do you? Absolutely no idea. Okay. This is what the output would look like. I'm just going to round and say that's 1, 2, 3. So in this case, you would do y hat equals, our constant is 1. Question number was our x, so the coefficient on x is 2. So this is question squared, so that would be 3x squared. We did 2 of these. No idea? Does this make sense now, though? Okay. Okay. The rest of this stuff you don't need to know just yet. That's the line that we just found. Okay. We also have to remember how to interpret slope and y-intercept. Okay, before you write these down, do we realize that when you find a least squares regression line that it's based off of a sample? That you don't have the entire population, you have a sample, and that's where you came up with your line? Okay. So for our slope, so we end up with something like this, y hat equals a plus bx. Okay, this is a prediction of the population line. So this is really the sample regression line. Our population regression line looks like this. So in other words, the slope that we found is just an estimate of the population slope. The y-intercept that we find is just an estimate of the correct y-intercept. That's why when you interpret slope and y-intercept, you have to say predict always, because these are not the true values of the parameter for the population. They just come from a sample. So slope is the predicted increase in y when x increases by 1. So in context, we predict that when question number increases by 1, that the percentage of students answering the question correctly is going to decrease by 0.932. And then the y-intercept is the prediction when the question is 0, we estimate that 84.9% of students will answer the question correctly. Now, does that make sense? No, we talked about how oftentimes your y-intercept is not going to make sense. Why is that?
And we have question 0.
We don't have question 0. What do you call it that the y-intercept often doesn't make sense? What is that vibrating? Is it a phone in the wall? Okay.
Might be a cat.
We talked about how oftentimes your slope is meaningful, but your y-intercept isn't. Why? Why is your y-intercept oftentimes not meaningful?
Usually it's outside the domain.
Yeah, what's that called?
Is that extrapolation?
Extrapolation. So extrapolation is when you use your model for an x value outside of the domain of the x values or of the data set that was used to create the model. So in our case, our model had question numbers 1 through 35. So our model only applies to question numbers 1 through 35. So question 0 outside of the domain, that's why it doesn't make sense. All this stuff sound familiar?
Yes.
Okay, but it's really important that you understand that our regression line is just an estimate of the population line. And we don't actually know the population line. Okay, this is the stuff that's new. So this is on page 9. Okay. So we talked about how you have this least squares regression line based on your sample, but oftentimes that regression line doesn't go through every single point in your sample, right? Okay, so then you have what's called a residual. So what is a residual? It's the error. It's the difference between the value that actually happened and what you predicted. You guys know what I'm talking about? So it's y minus y hat, y being what happened, y hat being what we predicted. Okay, so there are very important properties about these errors. The first one is that they have a mean of 0. So no matter what, those errors are always going to have a mean of 0. The way to check that is by looking at a dot plot or a histogram. Now that's going to happen because some of your residuals are positive and some of them are going to be negative. Some are above the line and some are below the line. Second important property is that they have a constant standard deviation. The only way to check that is by a residual plot. Do you guys remember what is it? Residual plot plots?
Residuals.
the scatter plot, so it needs two variables, that's only one.
Isn't it the same x?
X versus the residual. So a residual plot plots X versus the corresponding residuals. What are you looking for in a residual plot? Right, you want a random residual plot. So all of these errors that I'm talking about are for a specific X value. So for this X value, the errors associated with this X value have a mean of 0. They also have a constant standard deviation between the different X values. The errors are normally distributed. Again, you're going to check that with the dot plot or the histogram. Again, for a specific X value. So for this X value, let's say that's question number 2. The percentage of students who answer this question correctly is going to depend on the test. So if I gave the test to you and another class, and another class, and another class, and I looked at what percentage of students answered that question correctly, it's going to be different by class. We agree? Okay, so if I were to graph those, do we realize for that same X value, that same question number, that there would be different Ys? Right? And then there would be different errors. Some classes would be much higher than what we predict, and some would be lower. Those errors between the classes for the same question number are normal, have a mean of 0, and a constant standard deviation. And then the last one is that they are independent. Okay, now these 4 assumptions are not always true of the regression model. They need to be true of the regression model. So when we start inference in the next section, these are the assumptions that you're going to be checking. Do you remember for 2 sample tests how we had to check that the samples were independent? And I said you're really never going to know that one. You're just going to say, yeah, it's true. That's the same with the errors being independent. It will never, ever, ever say the errors are independent. And that's one that you can't really check. You just have to assume it to be true. Does this make sense?
Whatever you want.
What I need you to know from this is I need you to have these properties memorized and how to check them. You don't need to understand why they're true. You just solely have to have them memorized and understand how to check them. Can we do that?
Yeah.
That's not that bad. Okay. This, I know we're flipping around a lot, I'm sorry. This is on page 8 again. Okay. This is a dot plot and a histogram of the residuals. The reason there's 2 of them is these are the residuals and these are the standardized residuals. Do you guys remember what standardized means? No? Anybody? Change it to a z-score. So here, these are just the normal residuals. Here are the residuals once they change into a z-score. Same thing up here. Here are the normal residuals. Here are them once they were changed to a z-score. So here we're looking. Does it look like the residuals are normally distributed? Yeah, maybe. Does it look like they're centered around 0?
Yeah.
Yeah. And that's all we need to be able to tell from that. Okay. These are these 4 graphs on page 8. 3 of the 4. So this is your original data set, and here are the 2 residual plots. So again, X versus the residual, X versus the standardized residual in this case. Residual plot, we're looking for random. Do these look random? Fairly random, I would say. So that means that our errors have a constant standard deviation. I will never ask you to find all of the residuals and then construct a histogram or a dot plot or a residual plot. I will give them to you. And you just need to be able to look at them and say, does my residual plot look good? Does my histogram look good? And then you have to have those properties memorized. That's all that's new from section 1. Fair? Okay, there's still a lot of stuff from the output though that I want to go over. Okay, all that stuff in red is the stuff that you need to understand what it is and be able to find it. Okay, A, what does A stand for? went over this. What's A stand for? Y-intercept. And B is our slope. You guys have this on some page, don't you?
I don't know. Oh, that's 11?
Yeah, no, it's on page 8.
Eight?
It's the top of page.
Yeah, it's the top of page 8. I'm just really jumping around. Trying to keep you guys on your toes. It's the top of page 8.
I'm on my butt.
You don't have the red stuff, but you have the output. Okay, so up here is where you see your regression equation. So this is our y-intercept, so that's A. This is our slope, so that's B. R and R squared. What does R squared stand for? What's the word?
Correlation.
Coefficient of determination. R squared is your coefficient of determination. Now they give you two R squareds. They give you R squared and R squared adjusted. R squared adjusted you're never going to use. You're always going to use this R squared. So this is R squared, coefficient of determination. R is the correlation coefficient. Correlation coefficient, they never tell you. So if you wanted to find R in this case, you're going to take the square root of 41%, so the square root of 0.41, and then you have to remember that's going to be negative. It's always up to you to determine the sign of R. In our case, our B value, our slope is negative, so our R has to be negative. Okay, SE. You guys remember what that stands for?
Standard edge.
Standard error. Yeah. So that's this right here. It's just listed as S. If you wanted to find SE squared, you would just square it. Oh yeah, imagine that.
It's uncanny.
Okay. Next one, estimated standard deviation of B. This one, I don't think you guys have learned before. But that's this right here. The standard error of the coefficient. We want the one that's next to slope. This is our slope. So this right here is the standard deviation of B. It's written like this, S sub B. So that's the standard deviation of B, or the standard deviation of the slope. Okay, this is probably the most confusing one to remember, degrees of freedom. So obviously you know to look at the degrees of freedom. This number right here is the total degrees of freedom. It is not the total sample size. So this last number is n minus 1. So our sample size is 35. Okay, SS resid and SSTO. So residual error, this is the SS resid. So 4452.1. SSTO goes with total. So that's the 7550.7. Do you guys remember when to use those? They're really only used for one thing. One formula. No. The coefficient of determination. It's the R squared equals 1 minus SS resid over SSTO. I'm never going to ask you to calculate them. At most, I'm going to ask you to find them in the output and use the formula. Same for the AP test. The residual sum of squares is used in one other formula. Do you guys remember the other formula it's used in? Standard error. The SE. That one's the square root of SS resid over n minus 2. Neither of these formulas are on the formula sheet, so these you have to memorize. And then the last thing in this output are outliers. So it gives you unusual observations down at the bottom. And it says, these denote an observation that have a large residual. Large residual means that it's an outlier. So in this case, there are 3 outliers. Question number 19, question number 20, and question number 33. Questions? No? We ready to keep going? We have more. I know. I can erase?
Go for it.
Okay. You have to know how to interpret R squared, the difference between influential and outlier, and then extrapolation, which we talked about. Do you guys remember how to interpret the coefficient of determination, or R squared?
Yes. It's the percentage of y that's like determined by x, right? Something like that, kind of like.
Yeah, but more complicated terms. This is that sentence that I told you to memorize, so I think I have it. Okay, let me say it and then write it down. It's the percentage of variability in y that can be explained by the approximately linear relationship between x and y. So approximately 41% of the variability in y, in percentage correct, is explained by the approximately linear relationship between question number and percentage correct. Okay, so for panic and phantoms, I've told you guys those last sentences you need to memorize. This is one of those sentences you need to memorize as well. Don't try to wing it. Don't word it your own way. I want it worded exactly my way. So what this is saying is about 41% of the time, y changes because x does. The other 59% of the time, y changes for some other reason. So R squared is again a measure of strength for a linear relationship. So the closer that R squared is to 1, the more linear the relationship is. So R squared is not very close to 1 at all, which means that this is not a very strong relationship. Okay, do we remember the difference between influential and outliers? Outlier is far in what direction? The y direction. It has a large residual. Influential is far in what direction? X. How do you check for an outlier?
1.5.
You don't. How do you check for influential?
Take it out, slope changes.
Remove the point, do the regression again. It should change the slope or R significantly or both. If it changes them a little bit, but it's not a significant change, then the point is not influential. Do we need to talk about extrapolation again? No. Okay. Okay, this is really important. So SE is the standard deviation. Can we talk about this before you start writing? SE is the standard deviation of the residuals. So it's the typical residual. Remember that a residual is how far your point is from the line. So SE really tells us about the fit of the model. It tells us typically how far the point is from the line. So in this case, we estimate that observations in percentage correct, so in the y direction, typically deviate from the population regression line by 11.62 percentage points. So SE, because it has to do with residuals, residuals only have to do with the y direction, have nothing to do with the x direction. So that's SE. So write that down and then stop before you start writing SB. Or you guys write SB too, and then we'll talk about it. So, do you remember how we talked about like 10 minutes ago that you are finding the sample slope and that's just an estimate of the population slope? Okay, so we realized if we took a whole bunch of different samples, we would get different sample slopes. So based on one sample, we are able to estimate the typical deviation from sample slopes to the population slopes. Okay, so this SB is based on all possible samples. So if I took every single sample and found all of their slopes, this would be the typical deviation of that sample slope from its actual population value. So it's very important that you understand that SB comes from all possible samples. SE comes from one sample. So SE looks at all the residuals in one sample. SB looks at all sample slopes. Okay, in all reality, we only have one sample. So SB is estimated off of our one sample. Multiple samples, although we only use one sample. How do we feel about this?
Gucci.
Okay, we have one more question to do. Okay, can we move on? Okay, this is on page 10. Okay. So it says, consider the least squares regression line below. Y hat is 23,000 plus 47x. X is the house size in square feet. Y is the house price. Take your standard deviation to be 5,000. It says, what proportion of 1,800 square feet homes would be priced over 110,000 and under 100,000? Okay. So to start the problem, it tells us that we're looking at 1,800 square feet homes. That's our X value. We can probably guess that we should substitute that into our regression equation. So we have y hat equals 23,000 plus 47 times 1,800. I have no idea what that is. Really? I got 107,600. Yeah. Okay. So this is the predicted price, or it's going to be the average price for houses of this size. Now we want to know what proportion of the houses are going to be over 110,000. So we're looking for the proportion of houses. Proportion of houses that have a price over 110,000. So you're just going to convert this to a z-score. So you have 110,000, subtract what you would expect, so that 1,700, or 107,600, wow. And then use a standard deviation of 5,000. So I got a z-score of 0.48. Do most of you use the calculator for this and not the table? I think most of you do. So you're going to do normal CDF. Our lower bound is 0.48. Our upper bound is 1 times 10 to the 99th. Mean of 0, standard deviation of 1 since it's a z-score. I got it to be about 0.3156. So about 31.5% of homes are going to be priced over $110,000. Question. Why am I allowed to use the z-score here? Okay, I gave you the population standard deviation, that's true. But that's not the reason. Why is it normally distributed? Remember how we talked about errors are normally distributed? I said that that's one of the assumptions. That's why you're allowed to use the z-squared here. Because in the linear model, the errors are normally distributed. Questions? I think that might be it. Whoa, look at that.